Today, we're going to break down an absolutely brilliant method for sharing secrets. It was dreamed up way back in 1976 by Whitfield Diffie and Martin Hellman. And honestly, its genius is in how it solves what seems like a totally impossible puzzle. So, think about this for a second. How can you and a friend agree on a secret password? If you're in a crowded room where literally everyone can hear every single word you're saying, you can't just whisper it. It sounds impossible, right? How do you do it? Well, this isn't just some brain teaser. This is a problem our internet has to solve millions of times a second just to work. Every single time you see that little lock icon in your browser, something just like this has to happen in the background. It's absolutely fundamental. Now, the really cool part is that the solution, the Diffie-Hellman Key Exchange, is actually super intuitive once you see it. And believe it or not, the best way to get it has nothing to do with computers. It's all about mixing paint. Yeah, seriously, paint. Okay, so let's walk through this whole paint mixing puzzle together. Forget all the math and the code for just a minute. Just picture some cans of paint. So here's how it goes. First, we start with a public color that everyone can see. Let's say it's yellow. Now Alice and Bob each pick their own secret color that nobody else knows about. Alice picks red, Bob picks blue. They each take some of that public yellow and mix in their secret color. So Alice gets orange and Bob gets green. Now they swap their new mixed colors right out in the open. Here comes the magic. Alice takes the green mix she got from Bob and adds her original secret red. At the same time, Bob takes the orange mix he got from Alice and adds his secret blue. And boom! They both end up with the exact same final color, this sort of muddy brown, without ever having to reveal their original secret red and blue colors. Pretty clever, huh? What is so brilliant about this is that this simple idea of mixing paint translates perfectly into some really powerful math. So, let's pull back the curtain and see how this visual puzzle actually builds the foundation for real-world online security. Okay, so check this out. Every piece of our paint analogy has a direct mathematical counterpart. That public yellow paint, that's actually two public numbers that everyone knows. Alice's secret red paint and Bob's secret blue, those are their private keys, just secret numbers they picked. And the mixing, well, that's a special kind of math called modular exponentiation. It's basically a one-way mixing function for numbers. The public orange and green mixes are their public keys, and that final shared secret brown, that's the shared secret key they both calculated, all without ever sending their private keys over the wire. So here's what that looks like in practice. First, everyone agrees on a big prime number p and a base alpha. Those are public. Then, Alice picks a secret number, a, and she calculates her public key a. Bob does the exact same thing with his own secret number b to get his public key b. They then swap a and b right out in the open for anyone to see. Now for the final step. Alice takes Bob's public key, b, and raises it to the power of her own secret, a. Bob takes Alice's public key, a, and raises it to his secret, b. And because of how the math works, they land on the exact same final number, k. That's their shared secret. Let's make it real with some simple numbers. Let's say the public prime, p, is 29, and the base, alpha, is 2. Alice secretly picks the number 5. So she computes 2 to the power of 5, which is 32, and finds the remainder when divided by 29. That's 3. So she sends the number 3 to Bob. Meanwhile, Bob secretly picks 12. He computes 2 to the power of 12 modulo 29, which comes out to 7. He sends the number 7 to Alice. Okay, ready for the magic? Alice takes Bob's 7, raises it to her secret power of 5 modulo 29, and gets 16. Bob takes Alice's 3, raises it to his secret power of 12 modulo 29, and he also gets 16. It works. They both arrived at the secret number 16 without ever revealing 5 or 12. So this all leads to the big question, right? If an attacker is listening in and sees all the public numbers, why can't they just work backward and figure out the secret? Let's jump back to our paint analogy. An eavesdropper has the public yellow paint. They also see the orange mix and the green mix being swapped. So why can't they just, unmix the paint? Why can't they look at that orange paint and figure out exactly what shade of red was added to the yellow to make it? Well, because it's really hard. The security of this whole thing hinges on a concept called a one-way function. It's easy to do in one direction, but ridiculously hard to reverse. Think about it. It's easy to mix two colors of paint, right? But it's practically impossible to separate them back out perfectly. The mathematical version of this is called the Discrete Logarithm Problem.
Knowing the final number, the base, and the prime, it's just brutally difficult to work backward and find that secret exponent. That's the unbreakable lock.
So an attacker knows the public numbers P and alpha. They also see the public keys A and B as they're exchanged. But to break the whole system, what they need is one of the secret keys, either Alice's A or Bob's B. And to get that, they have to solve the discrete logarithm problem. The entire security of this whole thing rests on that one mathematical problem being incredibly hard to solve. And this is basically a constant arms race. As our computers get faster and more powerful, we get better at solving the DLP for bigger and bigger numbers. You can see here, back in '91, a 193-bit number was cracked. By 2007, that number jumped all the way to 532 bits. So to keep our secrets safe, the numbers we use just have to keep getting bigger and bigger. And that brings us to where we are today. The current gold standard for long-term security says that the prime number you use, that big number P, needs to be at least 2048 bits long. We're talking about a number so gigantic it's almost impossible to comprehend. And trying to solve the DLP for a number that big is, for all practical purposes, impossible with today's computers. So this all feels a little abstract, right? This piece of math from the 70s. How does it actually connect to the stuff we do every single day? Let's take a look. The short answer is it's everywhere. It's a fundamental part of things like SSH, which lets people securely log into servers. It's in something called IPSec, which creates secure network connections like VPNs. But the big one for most of us is TLS, or Transport Layer Security. That's the protocol that puts the S in HTTPS and gives you that little comforting lock icon in your browser's address bar. But here's a really important thing to remember. Diffie-Hellman itself doesn't actually encrypt anything. Its one and only job is for Alice and Bob to agree on that secret key. Once they have it, they then use that key with a totally different, heavy-duty encryption algorithm to actually scramble their messages. Think of it this way. Diffie-Hellman secretly agrees on the password for a safe. Other algorithms actually put the stuff inside the safe and lock it. All right, so let's quickly recap the big ideas here. First, Diffie-Hellman is all about key exchange, creating a shared secret out in the open. Second, its security comes entirely from how hard it is to solve the discrete logarithm problem, which is just like trying to unmix paint. Third, the size of the numbers you use is everything. You need huge keys, 2048 bits or more to stay safe long term. And finally, it's not the end of the story. It's the critical first step that sets the stage for other encryption systems to do their job. And that leaves us with a really fascinating question to think about. This elegant piece of math from the 1970s is still protecting our secrets online today. But what happens when computers get a whole lot smarter? I'm talking about quantum computers, which might just be able to crack the discrete logarithm problem for fun. What happens to our secrets then?